Well, now that we know about the domain and the asymptotes on a function, we're ready to graph a rational function. So we have the function f of x is equal to 4x divided by x squared minus 1. There's a series of steps that we're going to follow as we go through the graphing of this function. The first one we're going to look for is, can I factor and then reduce the function that I'm looking at? Well, 4x and x squared minus 1. There's no way that I can factor this any further and reduce it, so in this particular case, I don't need to do that step. Now the next thing I'm going to look for is I'm going to check for symmetry in the function. When I'm sketching the graph, it might be helpful for me to know whether or not we're symmetric around the origin or the y-axis. Remember that when I check for symmetry, if I replace x with a negative x, and let's say I come out with the exact same function I started with, we have symmetry around the y-axis. If I replace x with a negative x and I come out with all signs opposite of what we have, or a negative f of x, I have symmetry around the origin. Now what would, if I'm looking at the same function, then that's kind of easy to recognize. But symmetry around the origin on a rational function, what would I be looking for here? Well, if I have symmetry around the origin, then the rational function's signs would be opposite. So I can either have a negative 4x in the numerator with the same signs at the denominator, or I can have a positive 4x in the numerator with a negative x squared plus 1 in the denominator. Because either the numerator or the denominator's signs will change, not both, in order for that to occur. So let's go ahead and substitute in negative x and see what happens. That's a 4 times negative x divided by negative x squared minus 1, giving me negative 4x divided by x squared plus, x squared minus 1. That is this first case scenario, so that tells me that I have symmetry around the origin of this function. Okay, now that we know we have symmetry, let's talk about finding the x and the y-intercepts. When I find the x-intercepts of my function, that's where I am going to set the function equal to 0 and solve for x. So we're going to do that one first. Remember that my function was 4x divided by x squared minus 1. We're going to set it equal to 0 and solve for x. I do that by, let's see, I can think of it multiplying both sides by x squared minus 1. That's one way to think of it, because that x squared cancels with that denominator. This leaves me with 4x on the left and just 0 on the right, because 0 times anything is 0. So x, divide both sides by 4, and x is equal to 0. In other words, when x is equal to 0, y is also equal to 0. So I have an intercept occurring at the origin. Now we need to come in and look at the y-intercept of a function. When I'm looking at the y-intercept, that's where I set x equal to 0 and then solve. Okay? So if my function was 4x over x squared minus 1 equals y, then I'm going to replace x with 0. So 4 times 0 divided by 0 squared minus 1 equals y, or 0 divided by negative 1. Well, 0 divided by anything is just 0. So 0 is equal to y. So when x is 0, y is 0. That really only, finding the x and the y-intercept of this particular function only gave me 1 point, and that's sometimes the case when it passes through the origin. The next thing I want to be able to look at are the asymptotes. So remember that we have vertical and or horizontal slant asymptotes. So my vertical asymptotes occur when the denominator is equal to 0. So again, I have the function 4x divided by x squared minus 1. So I'm going to take the denominator, set it equal to 0, and solve. I add 1 to the right-hand side. That gives me x squared is equal to 1. Take the square root of both sides, and I find that x is now equal to a positive and a negative 1. So I have asymptotes, vertical asymptotes, at x equals positive 1 and x equals negative 1. Now, let's talk about the horizontal or slant asymptotes. Remember, I can't have both. I have one or the other. If my function is 4x divided by x squared minus 1, this is when we are going to look at the degree of the numerator versus the degree of the denominator. So the degree of the numerator is 1, the degree of the denominator is 2, and 1 is less than 2. When I have that occurring, when the numerator is less than the denominator, we have a horizontal asymptote at y is equal to 0. Go back and look at your rules for that if you can't remember. So now I have lots of information for me to be able to sketch my function. So I'm going to sketch the intercepts and the asymptotes here. So I'm going to draw my x-axis and we're going to graph something. Okay, so I've drawn a grid so that I can sketch my asymptotes and my intercepts first. I know that I had vertical asymptotes that were occurring at negative and positive 1. So I'm going to come in here and draw a dashed line at x is equal to a negative 1 and one over here when x is equal to positive 1, because we found those out. I also know I have a horizontal asymptote occurring here at y is equal to 0. The other thing I know is I had an x and y intercept occurring here at the origin. After that, I don't really know what I have, but I'm going to go ahead and I'm going to put my function into my graphing calculator at this point. So I've already done that. And if you come over here, I've got it graphed in the on the y equals. Remember that when you're graphing a rational function, the numerator and the denominator should be surrounded by parentheses so that you're telling the calculator to graph it correctly. So when I go and see the graph of it, I've got a curve over here in the third quadrant. I have a little, I don't know, curve right here coming right around the center and the origin. And then I have another curve over here in the first quadrant. So I can sketch that on my graph as it is. If I come in here, I know that I had this little jog right here passing through the origin like we discovered. I've got something happening over here in this third quadrant, but you know that we are kind of bounded, so to speak, by these asymptotes on the horizontal, or y equals 0 and x is equal to negative 1. And then we have this other boundary from asymptotes occurring up here. Now that's probably all I need. If I wanted to get a little more particular with my graph, I might be asked to find some additional points to just sketch it if I were sketching it by hand to make it look really nifty. You are going to be asked to do this on the computer, so let's go through how I might find these additional points. I know that I have an asymptote here, and I might want to find what's going on, what are some points to the left of that asymptote. So let's say that I want to know what the graph looks like. How close is it to the y equals 0 at negative 4? I also have something going on in here inside of these two asymptotes around the origin. So maybe I want to know what happens when x is negative 1/2 and what happens on the right hand side when x is positive 1/2. And then we'll just repeat that idea over here. I want to know what happens when x is equal to a positive 4. Because I already have the function entered into my calculator, I can use the table function to find out what these values are. So if I pull up my calculator, and remember that my table function is set to ask. The independent variable is set to ask. So when I do second table, it asked me to enter a value for x, which I put in at negative 4, and it gave me that the y value was a negative 1.2. 0.07, we'll call it. So I can quickly come up with the y value in an ordered pair if I'm given x using the table function of my calculator. Now, why would I want to know how to do this? Again, if I were asked to sketch something like this by hand, these additional points might help me get my curve just a little bit cleaner. And on the computer, you're going to be given the x values, so you won't have to come up with those on your own, but know that you can just plug them into your function to come up with the y values. This is what the sketch of my function looks like, and that's how we're going to graph our rational functions.